Okay, cool. Share screen. Good. So if you scroll all the way to the bottom of, is this us? No, this is another class. This one's us. Okay. So if you scroll all the way down to this one, I'm going to, this was a, let's see, yesterday I sent an announcement to, this is the announcement that you guys will get in just an hour as soon as this Zoom link comes to my email. This is what I wanted. I need that for right now. Okay. Question. Yeah. So this was the thing I put in the which I will send to you guys in an hour or so when the link comes to my email. But I just wanted to point it out that it's also down here where you can find like the link to Lab Zero. This was the very first announcement we got, like when we first started. And here's this thing right here, which I'm going to use in this intro as well, just to give you some advice on. So it either looks like this, and you can click the PDF button right here, recompile, and then you'll see what it looks like in normal wording. This is in particular what I'm going to use in a little bit. Or sometimes if you click the split screen, usually I think this is the default. So here's where you write stuff. Like, let me show you what this looks like. It looks like that. So this language is the same as this. Anyway, we'll use it in a second, but I just wanted to point it out. Okay, announcements. Good. Let's head over to the lab manual, which, interestingly enough, the background or like the theory of this lab is totally irrelevant for well, it's not irrelevant. It's describing physically what's happening in our circumstance. We turn this air on, we collide things. It's like our own little controlled billiard ball collision. However, what we're going to do in the experiment is find, let me just explain or show you what the experiment looks like first. Yes, let's do part one. Okay, so here's a video of what the experiment looks like. I make sure that both of my carts fit in between my photo gates. For part one, you can see that they want us to start off, or I don't know why they call it part one is preliminary. So the real part one or part two is I put my giant cart in the middle and I throw a small cart at it. So I make sure both of them fit in, and I do that because I want this to pass the photo gate. So what's happening here is we're getting the velocity of each of the carts before and after the collision by using the photo gate, which will give us a time on Logger Pro, and the width of these things. They're called flags. That's what they call them in the lab manual anyway. So we use the width of that, which we measure. We get the time that it took for the cart or the flag to pass through that laser. And from that, distance divided by time, we get velocity. So here's what it looks like. I'm collecting data now. I throw it in and it passes through. So what did I get there? The initial big red cart was not moving at first. So it's at rest. So there is no initial velocity for that. That's going a little bit too fast. From that, I get the initial velocity of the small cart. And then from the other photo gate, this red one, I get the final velocity of the large cart. So data point 1, data point 2, and then right now we're going to see data point 3 come right there. That's the final velocity of the small cart. So we have 3 for every single collision that we have, whether it's part 2, 3, or 4, we have 3 pieces of data. And what it looks like in Logger Pro is this. So this one is the small cart happening. So based on you have to view things very like chronologically for this lab. So this happened first, this happened second, this happened third. So the first thing that happened, and another way to determine which photo gate is which, is you just turn on the photo gate and wave your hand or move the cart, because you can just move it back and forth. So what I did was I started collecting data. I took my small cart and just wiggled it in front of this laser. and all I collected was data from this one. So I know that state 2 corresponds to this one, this rightmost photo gate for me. It may be different, like it really just depends on which wire is connected which. So you just have to do that as you're moving along. So what does this say? This tells me that this is the time that the cart started, the flag started to block the laser. And the next time below it is the time that it stopped blocking the laser. So what I do is I take delta t, which is just the time in, or the first time minus the second time, or vice versa. If you don't want to have things with a minus sign, that minus that. And then I take the width of this thing, and then I use velocity is distance divided by time. And so I get the velocity. So I do this for each of them. This one would be the initial velocity of the small cart. This one would give me the final velocity of the big cart. And this one will give me the final velocity of the small cart. And the other thing that you have to do, which they mentioned to you in the Google Sheet, is to keep your eye on the direction. So what happened in my first one? My small cart, I guess you can just view these as arbitrary. I just define them like, so this is moving. I can't really tell how you guys are viewing this on the Zoom. Let me try this. So the small cart is coming in to the right. This goes to the right, and then this reflects back to the left. So if I write those directions down, this one was going to the right, this one was going to the right, and this one was going to the left. The right or left doesn't matter as long as like there's a you keep track of a change in direction. So you could also say this left, left, right. So as long as two of them are positive and one of them is negative for this part at least. So now that we understand so that's the whole lab. You just keep track of things like that. But the funny thing is, if you notice, we already found final velocity for both of the objects. We found final velocity here and final velocity here. We did that ourselves with the Logger Pro. But what the lab gives you, these equations right here, are how to do it if you were given it on an exam or something like these. So yes, these equations are very helpful for like an exam formula sheet, but we're actually doing them. So we actually have this information, and our whole objective in lab is to verify these equations. So momentum, so P is another word for momentum. P equals momentum. KE is kinetic energy, and we know the formula for that, 1/2 mv squared. And P is mv. So our whole objective in lab is to say, is momentum conserved or is energy conserved? So we take the initial momentum, Pi, and ask, is that equal to Pf? That's the whole, that's the whole objective. I don't know why that, oh, right. That's really the whole objective of, is momentum conserved or not, or is energy conserved or not. The same thing you can do with, is KE initial equal to KE final. So these equations, where they come from is using conservation of energy and using conservation of momentum. For this one, we use both. Conservation and momentum are conserved in an elastic collision, which means the two things bumper cart together. So these little pieces of metal do not stick together, so they use very little energy when they smash together. However, what we'll do in the very last part is an inelastic collision. These collide, and the Velcro, the molecular energy, bonding energy, you can kind of call it, is used, and so energy is not conserved because there's some energy needed for that to happen. That sticking together costs energy, and so you lose energy, and these two things travel together. Yeah, a lot of people were confused about. Usually, the whole point of this background section is we use these equations and verify them. But really, the only equations we're verifying is PI equals PF. P, again, is that other word for momentum. Right, so this is the equation for that. Or I can just find it over here, which because we are not using these equations, I thought it would be, I can derive them if anyone would like. This one is very easy. It's just momentum, so you're only using one equation. However, for this one, you're using two equations. Momentum initial equals momentum final, and energy initial equals energy final, which is kind of non-trivial. And so what I'm going to do in the announcement is send you guys a link to someone who does it very well. This is the most succinct, easy to understand way I could find it. This is what momentum conservation means. This is the momentum of the first cart before the collision happens. That's what I means, initial. This is the momentum of the cart 2 before the collision happens, or the I, and similarly for the F, final and final. And momentum is just mv. Same thing for kinetic energy down here, 1/2 mv squared, 1/2 mv squared for both of the carts. And they do a really good job of just using it with algebra. So this is easy to follow, much more easy to follow than some other things. If you look on Wikipedia, they use something called the center of mass frame, which is just way too difficult to understand, in my opinion. And so I really like what this person did. So I'll send it to you guys. And yeah, the only reason I'm doing it is because we don't need those equations for the lab. They are good to know, you know, on our formula. I'm sure you guys are used in a variety of homework or tests or something like that. So we won't need that. That I'll send later. Let's give you some more examples of what's going on. Okay, so here, this will be, I think this is part 3. Yes, this is part 3. Yes, so this is conservation of momentum and energy. This is just momentum. This I already explained. This was like turning on your photo gate and just waving your hand in front of one of them to make sure which is which. Yeah, and this is what I'm going to explain right now. So part 2, the first part of the first collision, part 2 is the first collision, is rather easy. You don't need to do anything kind of special with your air tracks. However, part 3 is a little tricky when you have the giant or the small cart in the middle. Because this mass is so much more than this one, when this collision happens, this one is going to go flying very fast. So in order to counteract that, let me show you a video of what happens. What I usually do is I move. So you can see here, I kind of have things centered in the middle of my air track. But for this one, where the small one is in the middle, this is all the way to the end of my air track. So this has plenty of room down here to move around. Because what happens, even if I do it super lightly, that one sometimes will come back and hit that before I get data. So right here, when this passes uninhibited, that's good. So that was my last point of data. This coming backwards, if I had put this in the middle of my air track, it would have hit it and I wouldn't have been able to get data. For instance, that would have happened and it bounces back. So you can see it in my Logger Pro. The only ones I actually need are the first 6 cells. This was it bouncing back after it got hit. So I didn't click stop before that went through again. So what's happening? This is the big cart coming through the first photo gate right there. Then the next piece of data I get is from this one, the small cart passing through. That would give me the final velocity of that one. And then the next one going through the same photo gate. So as opposed to last time where it was gate 2, gate 1, gate 2, this one we have gate 1, gate 2, and another gate 2. Because if you see the next thing that happens, the large cart passes through itself. So large cart, small cart, large cart. And then I can just ignore this because that's all I need are 3 pieces of data for every single one. And six boxes give me that because I need delta t for each of them. So delta t is subtracting these 2 numbers, getting the difference between these 2 numbers, and getting the difference between these 2 numbers. And just for completeness, let me show you what the last part looks like when they stick together. I'll send it in and they stick together. So it's very similar to 2 in the sense that the first one goes in, but next, this one's kind of hard to understand chronologically because they stick together. This is the small part. This is the large part because of the order in which they went through. So again, large part, and then very quickly, small part, large part. So that's what things look like, and that's what the data looks like. And that should be all you need for this lab. Let me close this stuff. And I just briefly wanted to explain one of the uncertainties. And thankfully, someone asked me over email how to do this was for like the conservation of energy. So what I'm going to do is copy and paste this and explain how to do it for, like in particular, how to do this uncertainty. So you see, I have written 7, 9, and 11, and people get very freaked out when I have 3 things in the same one. So let me compare this to not last week, the week before, energy. When we did this uncertainty, it only had 7 and 9. The reason for that was because the equations that we were using to find that uncertainty. So let me just walk you through here. Here's the equation for kinetic energy. I take the uncertainty of it. The first thing I do, so from this equal sign to this one, is equation 7. Because this guy right here is 1/2, doesn't have an uncertainty. So it's just like the C from the error manual. Right, all the way too far, right there. So this is exactly equation 7, where C in our case is 1/2, and A is everything else. There we go. So C would be all that quantity. Then, now that we have this equation, we look at this thing and say, okay, we have that quantity right there. This is from last week. I don't know why that graph is in the middle of everything. So in order to get this uncertainty, we have this because this was already a cell that we were given. So this is our A and the uncertainty of A correspondingly right there. And if you notice, not only did we have the quantity for V, which we found, we also have a column for V squared. So because we already have a column for V squared and M plus N, this was just equation 9. This is A. It's so hard to highlight on my text. This is equation 9, where one of them is A, so M plus M is A, and B would be V squared, right there. And so all that we do is do the AB on the outside, AB on the outside, and then the square root of the uncertainty of A right here over A squared plus the uncertainty of B over B squared. The extra step here in our lab is that if you'll notice, there is no column for V squared. What you can do if you'd like to, if it's what I'm about to do is really hard for you to get, is you can take this column right here and make your own V squared column. So what you can do is say, okay, this is V squared, and this is uncertainty of V squared, and you can take your value, square it, and then use equation 11 right here to get the uncertainty of that. Because the uncertainty of a quantity squared uses 11. So it would be 2 the uncertainty of B. Or because they didn't give you your own column, you can do it in one fell swoop, which is what I meant by 7 plus 9. So let me type that out really quick. We don't have M plus M anymore, it's just M. B squared, let's get rid of this. Okay, what does that look like now? Can I get rid of all of them? Yes, okay. So this is the same exact step that we did for conservation of energy lab, but now we have this, which is the problem, because we don't, unless we do this, unless we make our own cell, we don't have that information. And so what we can do is use equation 11 inside this equation. So I'm going to focus on this thing I have highlighted. And add one more step. So I'm adding equation 11, which is right here, sigma of v squared, which I know by equation 11 is 2v sigma of v. So that is all of the equations together. Right here, I used equation 7, I'm taking out the 1/2. Here, I'm using equation 9. Both of those things are a and b. And then right here in this special case, so these are almost the exact same equations, but right here, I'm using equation 11, 2v uncertainty of v. I hope that makes sense. Again, this will be, it's all the way in the back, like at the very first announcement I sent out, but I'll send it again in that announcement. So yeah, data is pretty easy to collect for this one. And I think that is all. And yeah, as soon as this comes to my email, I'll send it out. And yes, of course, I will turn the air on.